All right, students. Moving on to the next. Oops. Moving on to the next section, we're going to talk about univariate data analysis, which is basically what we were talking about in the first chapter of the regular statistics lectures. And now I want to talk some more about how one works with vectors. Vectors are kind of a key object in R, probably not the most important object in R, but very important. They're used regularly throughout R and are kind of the ideal data structure for representing univariate data. So vectors loosely are just lists of objects. So for example, I can create a vector such as a numeric vector, and the numeric vector will have all of the numbers that I passed it in, stored in it. So here I created a vector called numvec. Numvec has the numbers 10, 13, -1, 0.02, 0.00, and -3.31. By the way, now is the time for me to describe what that little 1 at the beginning means when it prints stuff out. That is a way for R to print vectors out to you, and often vectors will have to be printed out over multiple lines. So if we were to have actually a long vector, I'm going to make a longer vector. The numbers at the beginning of the line are an ATU to let you know the index of the object that are first printed on that line. So the first index, the object in the first position is going to be the first thing that's printed on the first line. The object in the 36th position is what's printed as the first thing on the second line, and the thing on the 71st position. I could actually make it a little bit more obvious. So let's say 100 to 200. Yeah, so the object that's in the 36th position is going to be printed first on the second line, and what's on the 71st position is what starts the third line. So that's what that little 1 means when R is printing stuff for you. So, all right. R vectors can store actually a number of different things. For instance, I have a vector consisting of numeric stuff, but I can also have a vector of character data, and I can have a vector of functions. Functions in other programming languages are different. R handles functions very specially. It is in fact legal to have a vector of functions, because functions are essentially a special type of data. Now, that said, the C function that you see here is kind of the key function for creating vectors, but actually what C means is concatenate, so C for concatenate. And by default, R concatenates stuff into vectors, but if you were to pass C other vectors, it wouldn't create a vector of vectors. It would instead flatten the vectors that you passed it into one vector. So this command right here didn't create a vector of 3 vectors. It just created one vector consisting of the numbers 1, 2, 3, 4, 54, 10, 2, and -6. Okay, so R actually generally stores stuff in vectors. So for example, the variable I'm a vector, it looked like I just gave it the number 5. So if I asked it to print I'm a vector, it will print 5. But when you ask R, is this thing a vector? The answer is yes, because R by default puts stuff into vectors. Okay, so vectors are lists of stuff in a sense. So how can we access the stuff that's in that list? Generally, you are accessing stuff using square brackets. So how can you use square brackets? First, you can access stuff with an integer. Now, in other programming languages such as Python or C, counting starts at 0. So the first element in, say, a C array or a Python list is the 0th element. R doesn't do that. In R, the first element is accessed with 1. So, for friendly let's create a vector called friendly vector. The first element in friendly vector is going to be the element in position 1. So we can do friendly vector 1, and that gives us the element in the first position. So you are allowed to access stuff via integers. So we could ask what's in the second position and ask what's in the third position. There's nothing in the fourth position, though, so R returns NA because there's nothing there. You are also even allowed to access stuff via negative indices. So if I do friendly vector -1, I get a vector with everything but what's in the first position. So when you plug in negative indices, you get the complement of whatever you requested, at least when you plug in negative integers. So you get the complement of that set. You are if you have a vector with named elements, and friendly vector does have named elements. The reason why is because if you look at friendly vector, we said when we created it, we said, see, John equals 1, and as a result of that, this is going to be a named vector with an element named John, and an element named Tony, and an element named Janet. If we print out friendly vector, what we see is that we actually see the names of the elements and also the values that correspond with those elements. So we can even ask this vector, what are the name? We can ask R, what are the names of the stuff of the vector, and it will tell us the names of the elements. So we can access stuff using integers, we can access using negative integers, and we can also access elements using the names by passing a string with a name to the vector. So we can ask what's in the Tony position, in a sense, or what's in the Janet position. We could, now that said, negatives here doesn't work because you can't take the negative of a string. So that unfortunately will not get everything but Janet. But you can even pass vectors of characters, a character vector containing named elements, and you will get the vector at those positions. So that's something that you can do. So you could even I wonder what would happen if I were to type in, so we got friendly vector and I ask for an element that doesn't exist, such as Frank. Okay, it gives me NA. So, and that's because it doesn't exist. You can also use booleans, where you put a true at every position that you want to include and a false everywhere else. And it's unlikely that you're going to create vectors this way. No, that you're going to access elements in vectors this way directly, where you're going to literally list out which ones that you want. What's more likely is you're going to create a Boolean vector and use the Boolean vector that you created to access the contents of the vector. And you'll probably see examples of that later. You can change the names of the vector's elements. So, for example, this friendly vector, it originally was John, Tony, and Janet, but now it's Jack, Jill, and Dick. So if I look at friendly vector, I now have a vector with different names. And how you do that is this operator that was this function that was retrieving the names for the elements in the vector is also a means by which you can change the names of the element in the vector. So the way you do it is via assigning to that. You use the assignment operator to change the names. And then if we were to ask for what's in the Jack position of friendly vector, that should be whatever's in the first position. So, and that is in fact the case. So that's a primer on how you access stuff in vectors, you can delete values by setting whatever's in that position in the vector to null. So, for example, if I wanted to delete what's in the dict position, I could say friendly vector. Well, actually, I probably should hold off on that because I'm probably going to use this in a second. Well, actually, let's create a copy of this vector. So x will be friendly vector. This is a copy of the friendly vector. It is not pointing to, in some sense, the original friendly vector. So here is now the vector x. If I were to say x in the first position is null, let's see. That didn't work. Well, for some reason that was forbidden. Wonder if I can do this. I guess you can't. Okay, I guess you can't delete that way. All right, never mind. I'm a fool. All right. Moving on. Past my foolishness. All right. So we can change. So let's. So that was before what I was talking about. Accessing the elements of a vector, but we can also change the elements in the vector. So we have friendly vector. So we have friendly vector as a reminder what's in it. We can change what's in the jack position to 16. Now, if we look at friendly vector, we see that what was in the jack position is now 16. We can change what's in the second position like so. And we can even add new values by referencing potential indices. So there's nothing currently in the fourth index. This is a length 3 vector, but we can add a fourth element like so. And as a result, this is what we get. And if we were to add, what are going to be the names for this new version of the vector? So the names will be what we had before, but we didn't actually give a name to the fourth element. So as a result, that name is left. It's the empty string, basically. There's nothing really there. So, but we can also create an element, the Danielle element, and assign something to it. Here's now what friendly vector looked like. That was placed after what was in the empty position. We can reference. We can say that the stuff in the 6th, 7th, and 8th positions, those are all going to be 12. And this is now what friendly vector looks like. We can even say, okay, well outside of the of the range of elements. Like there isn't a 9th, 10th, 11th, 12th, or so on. Those elements don't exist. Yet we're still allowed to assign something to the 20th position. Everything in between will become NA. Yet we still friendly vector. So friendly vector 20 is what we assigned. That's the number 18. But 19, which was never assigned, that's NA. So NA is actually a special value in R. There's multiple such values that are really special. There's NA, there's NA, there's null, there's inf, there's negative inf, and there's NaN. Those are special values in R, where NA is meant for missing values, and it's missing in almost in the sense that in a data set, a missing value could be missing. Whereas null, it seems like it's talking about missing values, but it's actually getting to like in the program itself, in R itself, the thing doesn't exist. That's so NA is almost like a feature of the data set, whereas null is almost a feature of the programming environment. Inf and negative inf represent infinity and negative infinity respectively, and NaN represents something that isn't a number. So if we were to do 0 divided by 0, we actually get NaN out of that. It means not a number, and often indicates that some inappropriate numerical calculation was done. And we can put NA, if we want, into our vectors to indicate that there's missing data in a data set. So R has a specially coded value for missing data. And if we want to get the elements of not finished that are not NA, the way we would do so, we cannot do, if we do not finished not equal to NA, that doesn't quite work. That doesn't get us what we want. We have to use a special function called is.na and feed that function not finished. And that function will tell us which elements of not finished are NA. And then if we want to negate that, we put an exclamation point at the very beginning, and that will negate the vector and tell us which elements are not NA. Okay, so this will be the vector of not finished, that where you have everything except for NA. Okay. All right. So the C function is one way to create vectors. It's a way for you to kind of by hand create vectors, and you can create any vector you want using C. The unfortunate thing, though, is this isn't going to create every vector, and like it would be a huge pain if you had to use C to create a vector with 100 elements from the sequence 1 to 100. There is a much easier way to create a vector consisting of the sequence 1 to 100, and that is to use 1:100. And that will create a vector with the sequence 1 to 100. And actually, it can go in the reverse direction too. If you put 100:1, this will decrement until it'll decrement down from 100 all the way to 1. And you don't have to start at 1. You could start at 4 and go to 9, and 9 to 4, and so on. So this is ways for you. This is a way for you to create integer sequences of numbers where you're moving up and down by 1. So whenever you were seeing stuff like, for example, friendly vector 2 to 3, that was what was actually happening is you created a vector consisting of the numbers 2 and 3, or the numbers 2 through 3 if you want to be more general, and that vector was then passed to this subsetting operator, this square brackets, to then select elements in friendly vector. So that's how it was working. So this colon operator can be used to create sequences of numbers. There is a function called sequence that can create more, which is seq, that can create more general sequences of numbers. So for example, we could say sequence from 1 to 100. So we will put 1, 100. We can press enter, and that's created a sequence from 1 to 100. But we can even have more power than that. For example, if we wanted to count by 2, so we could say by equals 2. And now this will be 1, 3, 5, 7, 9, and so forth. Or we could say by equals 0.5, and now we're incrementing by a half. Or we can even tell it the length of the end result. So we could say length equals length equals I can't type. Length equals 1,000, and we'll get a vector with 1,000 numbers in it. Right. Actually, we should probably do 1,001 if we wanted something that was a bit. Oh, that's not quite what I thought it would be. Oh, so would I choose 99? I don't know. Something like that. But yeah, you can actually tell it how many elements you want in this sequence, and it will create a vector of equally spaced elements. So sequence is a great function to have in hand. There's a function called rep. So this is when you want to repeat elements. So we could say, so we have the numbers 1 through 3. We could say, repeat this, and the number of times is going to be equal to 2, and this will repeat that vector that many times back to back. So we get 1, 2, 3, 1, 2, 3. We could even, so to the times argument, we can have even more granular control if we pass it a vector. So we could pass it a vector and say, repeat the first element 2 times, the second element 1 time, and the third element 5 times. And it will create a vector where it's repeated in that way. There's also an argument called each. So this argument will repeat the elements in this vector that many times each. So instead of putting this vector back to back, it'll put it so that the numbers themselves are repeating that many times before it moves on to the next element in the vector. So I've actually got some example code down here that we could be using. Oh, by the way, and so the colon operator actually has a lower precedence than the parentheses. So you could do like 1 to whatever the sum of 2 and 2 is. So if you wanted to evaluate something first before using the colon operator, you could use the parentheses to make sure that something gets computed first. Here's a sequence, another sequence, here's rep, here's each. And another function useful for creating vectors is a function called paste. Paste will paste strings together. So we could do, for example, paste hello and world. And it will paste those two things together. You can control, by default, it's separating those elements with a space, but we can say sep equals whatever we want. So if we wanted to, we could put a $sign here, and it will separate the two strings with $signs. And how we could use this is we could give it one vector and then another vector. So we could give it hello and then 1 to 3, and it will paste those two vectors together. Now I wonder what would happen if we were to give it a character vector. So we've got hello and world. Okay, so what ends up happening is it will kind of alternate between. It will kind of try to weave the two vectors together when it's pasting. All right, so I have an example here with a treatment where I create. I like if you had 100 treatments, this would be really handy to have, because here I created a vector where I have treatment 1, treatment 2, treatment 3, treatment 4, treatment 5. And it was very nicely created with paste in an understandable way. But if I wanted 100 elements, that also it works just as well. So there's 100 treatments. Okay. Other things that you can do with vectors. You can do mathematical operations with vectors. Now, that said, if you're familiar with linear algebra, you probably have some thoughts on what matrix multiplication is, and you're thinking vectors are actually matrices. So when you do addition with a vector or multiplication with a vector, it'll do so like it would with a matrix. That's not what's going on in R. While R can understand a vector in the matrix sense from linear algebra, when it does addition, subtraction, multiplication, division, exponentiation, it's doing so element-wise. So, what do I mean by that? Let's say I've got this first vector, vector 1. Actually, that didn't quite work. So, vector 1. So, with vector 1, here's this vector. It has, let's see, I got 6 elements in it. If I do vector 1 plus 1, it will add 1 to everything in that vector. So, and if I do vector 1 times 2, it will multiply everything in that vector with 2. And if I do vector 1 raised to the power 2, it will raise everything in that vector to the power of 2. Okay, but what if we have vectors that are not of equal length? For example, we have vec2, and vec2 has 2 elements. What will happen is R will start recycling entries from the smaller vector when doing the computation. So, for example, vec1 has 6 elements and vec2 has 2 elements. So when I say vec1 plus vec2, R will start out by first adding the first element of vec1 and the first element of vec2. Then it will add the second element of vec1 and the second element of vec2. So it's going to do this element-wise addition. Maybe I should start out by first, there's this function called rev, rev allows us to reverse the order of a vector. So let's do rev vec1. So that's reversed the order of vec1, or produced a vector of reverse order with vec1. And I'm just going to make another vector with this. So let's call it vec3 will be rev vec1. Okay, so what would happen if I were to do vec1 plus vec3? What will happen is R will do element by element addition. So we'll add the first element of vec1 and the first element of vec3, the second element of vec1 and the second element of vec3, the third element of vec1 and the third element of vec3, all the way until it reaches the end. And this is the end result. And we could do that again with multiplication. We could do that with subtraction. We could do exponentiation and stuff like that. All right. What about when going back to vec2? What's going to happen when I say vec1 plus vec2? R will add the first element of vec1 and the second and the first element of vec2, and then it will add the second element of vec1 and the second element of vec2. Then it will take the third element of vec1, and there is no third element of vec2. So it will recycle. It will start recycling elements from vec2 going to the beginning of vec2. So we'll end up adding the third element of vec1 and the first element of vec2. Then the fourth element of vec1 and the second element of vec2. Then the fifth element of vec1 and the first element of vec2, circling back around to the beginning. And then the sixth element of vec1 and the second element of vec2. And that is in fact what you see. And it doesn't really matter the order in which you do it. R doesn't really care about the order when you're doing addition like this. And R will even do recycling when the shorter vector is not a multiple. Its length is so when the length of the longer vector is not a multiple of the length of the shorter vector. Like for example, I can divide by a vector with 4 elements. The only thing though is R will complain. It doesn't like it when you're doing stuff like that. So and so on. And in this case, we did not get the same result because exponentiation is not a commutative operation. Okay. Now that said, honestly, I hardly ever see recycling being used in programs, probably because it's confusing. Most of the time, people will add either vectors of the same length or vectors where one of the element or length 1 vectors, or which are basically just stuff. Right, so like for example, vec1 plus 1 is actually very easy to predict. You just add 1 to everything. Or vec1 plus vec1, also very easy to predict because you're going to end up adding the first element of vec1, the first element of the other vector, which is actually also vec1. But this element by element addition is very predictable. So So generally, you don't have to worry too much about recycling. It's kind of an exotic operation. Okay. All right. So those are vectors. What happens when you start giving functions vectors as inputs? Many of these functions are actually vector valued. If you're familiar with programming languages such as Java, such as C, such as Python, you may think that given a list of values, you have to write a thing called a for loop in order to be able to, if you wanted to take like the square root of everything, you would have to write a for loop that takes the square root of everything in that vector, going element by element through the vector, taking the square root of each thing in order, in sequence. Actually, you don't have to do that in R, because a lot of the functions that you would be using in R, for example, the square root function, they already, out of the box, work element by element. So, for example, if I ask for the square root of vec, it will take the square root of everything in vec. So we see the square root of 1, the square root of 2, the square root of 3, the square root of 4, which is 2, and the square root of 5. So a lot of these functions are vector valued, and as a result, you probably, I don't think in this class, I can think of an assignment where a student must solve the problem using a for loop. I don't think there's ever a situation where you ever need to use a for loop in this class. I mean, there are some times in R where you do need to write a for loop, but actually, most of the time you don't, because there's probably a function that's vector valued that's meant to work on vectors. So you can just like, if you want the square root of everything in that vector, just pass that vector to the square root function, and we'll take the square root of everything. If you want e to the power of everything in that vector, pass that vector to exp. These is dot stuff functions, they're often vector valued too. Like for example, is.na is vector valued. You feed it a vector and it gives back a Boolean vector. There are more operators in R that are vector valued. You could think of addition, subtraction, multiplication, division as vector valued functions, and that when you give them vectors, they spit out vectors. And it turns out that logical operators, such as we have double equals. So single equals means assignment. So this is actually something that students will often confuse. So single equals does not mean the same thing as double equals. Single equals means assignment, which is not the equality that we mean when we discuss mathematics. In mathematics, we mean when we say something equals something, it means those two things are basically equivalent. Assignment does not mean that. Double equals corresponds to the notion of equality that we use in mathematics. It's detecting whether two things are in fact equal to each other, and as a result, double equals will evaluate to either true or false. So 1 is in fact equal to 1, so this evaluates to true, but 1 is not equal to 2, so this evaluates to false. If we were to replace this with a single equal sign, we get an error because you cannot assign a number to a number. Okay? You basically have an illegal variable name. Other logical operators include less than, you have greater than, you have less than or equal to, you have greater than or equal to. You also have the AND operator, which means a logical AND. The OR operator, which means a logical OR. Not means negation, so not true is equal to false. And you also have this operator in, which corresponds to set membership. So for example, let's say I have a vector 1 through 3, or no, this is 1 through 34. All right, fine. I can ask whether the number 3 is in using %in%. Whether 3 is in this vector, and the answer is true. I could even go beyond that. I could say, is the vector 3 to 4 in 1 through 34? And what this will do is when there's a vector on the left-hand side, this in operator will first check the first element of this vector and see if it's on the right-hand side, then check the second element and see if it's on the right-hand side, and the third element, and so on. So for example, if I have the vector 4 and 100. 4 is on the is in the vector that's on the right-hand side, but 100 is not. So this will evaluate to true and false. To a vector containing true and false. Here's some more R code saying similar things. When you ask whether one vector is equal to another vector, it's not going to say are these entire vectors the same. Instead, it will go element by element through the vectors. So for vec1 and vec2, they are equal in the first position, but they are not equal in the second position. They are not equal in the third position. They are not equal in the fourth position, but they are equal to each other in the fifth position. So you get I'm not sure that I'm still recording, so I'm actually gonna I'm gonna pause for a second. Okay, I'm sure I'm recording now. I accidentally touched something and I'm not really sure what the effects of that was, so just to be safe, I started over recording. Where was I? Okay, so where I was, in the end, this double equals will, oh, hold on, I'm just going to double check. I really don't want to discover that I'm not recording. So, okay, we're good. All right. Um, so where was I? Oh, right. So, um, it ends up going one by one through each of these vectors and checking whether they're equal to each other. So you end up with true, false, true. Okay. Okay. So, you can do, for example, vec1 less than 4, and it will check element by element which of these elements are less than 4. We can do vec1 less than vec2, and it's going element by element, a lot like how I described equals was working, and so on. So we can negate what's in a vector. So for example, vec1. Oops. So vec1 less than or equal to 4 looks like this. This is a vector, and we can negate what's in this vector using the exclamation point. So that will give us the opposite of what we had. We can, let's see. So let's see. Here's another operator that I haven't talked about yet. I have the Modulus Operator. This represents all right. So 5 mod 2 is 1. What this corresponds to is if you take 5 and divide it by 2, what is the remainder? The remainder will be 1. 2 goes into 5 twice. So 5 mod 2 will be... So when 5 divide 2, if you were to not allow for... If you were to do like remainder notation, maybe you remember talking about remainders in second grade or something like that. 5 divided by 2 would be 2 remainder 1. So you would have a remainder. So 4 mod 2, that's going to be 0. So because when you divide 4 by 2, 2 goes into 4 evenly, so there's no remainder. So so as a hint, this actually, so you can detect whether a number is even by checking whether it has a remainder when you divide it by 2. So for this line right here, the region inside the parentheses is checking which elements of vector 1 are even. So this line right here can be read out as which elements in vector 1 are greater than 20 and which elements are not even. And when I run this line, I get false, true, false. And you can go and check yourself that this is an accurate representation of what's in that vector. There's also this OR operator and so on. We've talked about in. There's also a couple functions, any and all. Any will return true if anything in that vector is true. Remember that what we have passed to any, this part right here, this is a vector. Right? So it's going to check whether anything in that vector is true. All return, it checks if everything is true. So there is a true element in this vector, so this will evaluate to true, but there's also a false element, so all will result in false. Okay. Continuing on. Sometimes when you're working with Boolean vectors, what you want is not just whether something is true or false, but you also want to know where the trues occur. And there is a function called which that tells you which elements of a vector are true. So maybe going back to one of our previous examples, this example where we were checking which elements in vector 1 are greater than 20 and which elements are not even, if we wanted to know which the position of the vector, the positions in the vector where we had elements that were greater than 20 and not even, we could use the which function. All right, and it tells us that the element in the third position of this vector was true, and that's the number 21, which is greater than 20 and not even. Okay, so so this which function is often quite useful since it's telling us where the trues occur. And here are several examples of how you could use this which function. Here's another function that I haven't mentioned yet, length. So length tells us the length of a vector. So the length of 1 to 100 is 100 because there's 100 elements in this vector. The length of friendly vector is it is 20. It is 20 now. So let's consider this line right here, length which is .na data vector. Let's start out with is.na data vector. So that's going to be a vector consisting of falses and trues, and it's going to be true whenever an element is na. Now, let's consider which of those elements are in fact na. Okay. So those are going to be the elements in the 21st, 33rd, 49th, 61st, and 62nd position. And then I ask for the length. But I'm asking for the length of this vector that I just got, and so this would be a way for you to detect how many elements in this vector are in fact na. So there are 5 elements in this vector that are in fact na. Another way you could do this though without using length, it turns out that you can do true plus true. True plus true equals 2. True plus false equals 1. False plus false equals 0. True times false equals 0. Basically, true is 1 and false is 0. So, and in fact, in other programming languages, they basically say true is false and 1 is 0. That's what they are. They don't really have any other notion of true or false. The notion of true and false is really just to label something as Boolean so that you don't actually accidentally stick a 2 in there. The advantage of this is if you add up trues, if you add up Booleans, you get how many trues there are. So if I wanted to, for example, going back to this example, if I wanted to know how many elements were greater than 20 and also not even, I could add up the resulting Boolean vector, and there is a function called sum that sums up the elements of the vector it's been fed. So, like for example, sum 1 through 3 is going to be 6 because it's going to add 1, 2, and 3. And in this case, if you add up what's in is na, so so let's consider what's in here. So is.na is giving you true and false, and it's giving you true and false for whatever is na and whichever one isn't. If I wanted to know how many elements were na, I can add up this logical vector, and there were 5 trues in there, so it adds up to 5. That's actually a very useful property. Okay, continuing on. There's a special type of vector that I haven't discussed yet called a factor vector. Factors at some level represent categorical data. It's an R way to represent categorical data. So factors have a special internal representation, but you have the possible values and also which of those possible values are taken. So here I have this color data vector, and this is a character vector. And I could convert this into a factor vector using the factor function, and I tell it what the levels are going to be. Levels are possible values for the categorical data, in a sense. So then if I look at colcat1, I get blue, red, blue, 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 red, red, and so on. Basically, I have categorical data where the possible categories are red, green, and blue. So colcat2, by default, when I actually didn't have to tell Factor what the possible levels were, because it will guess what they are from a character vector. Here's the thing, though. In this color data vector, there was never green, so it won't guess that green is a possible is a possible level, which means that if I try to change the first element to green in colcat1, that's fine because that's a possible level, because we explicitly told it one of the possible values for one of these factors is green. But if I try that with colcat2, I get an error because that's not amongst the levels. So if I look at colcat1, I did in fact change the first element to green, but I didn't do it for colcat2 because green is not recognized for colcat2 as a possible value. In fact, what I got instead was NA, because it now doesn't know what to do. We can get the levels for vectors by using the levels function, and it will tell us what levels are possible. In fact, we are allowed to change the levels, and if we change the levels, we're actually going to change... in a way, we actually end up changing the data that's in the vector. The data will get rearranged in a way. So if we wanted to allow for the possibility of green in this second vector, we would have to add green as a possible level. And now we can change the first element to green, and that will be allowed. Okay, continuing on, we are now talking about functions. So functions are one of the most important objects in R. So important that R is actually called a functional programming language, because functions are allowed to be passed as data, in fact. You can treat functions as if they're data. So you can write functions. It's actually not hard to write functions, and in fact, if you're going to do if you're going to do stuff with R, you're probably going to end up writing a lot of functions yourself. So what are the key ingredients of a function? Functions have arguments and they have a body. So far, I've been working with functions, for example, square root, or maybe at some point you saw me work with hist. And so the arguments of a functions are the values that you pass to a function. So you can pass another term for this is parameters. You can pass stuff to functions, and it will work with the stuff that you pass it, and do some magic with it, and then hopefully return something to you. What exactly a function does to the parameters that you pass it, and by the way, a function doesn't have to have parameters. You can have a function that, for example, doesn't take any parameters, it just always returns 1. But functions generally have arguments. The vast majority of functions have arguments. Another important part of a function is a body. So the body is the code that the function executes internally and at some point in the body, you're probably going to return something. Functions don't have to return something, but they usually do. There are two possible ways you could return something. You could either use the return function explicitly to make it very clear that you are returning a value, and the moment the function hits return, the function's going to stop whatever it's doing, return, and then exit. Or you could, as the very last thing you do, have some call that doesn't get assigned to a variable, and since it doesn't get assigned to a variable, it gets returned. All right, so like for example, at the very end of the function, we can have 1 plus 1, and it will return the result of 1 plus 1. Okay, so to create a function, you use this syntax. My function, it will be assigned function, give it the arguments, then you have a curly brace, and then you have whatever's in the function body, and then you have a closing curly brace. So here is an example of a function. I created a function here called longest length. The function is supposed to take two vectors, x and y, as input. So it will return. So I have inside this function some local variable definitions that if I run this function, these variables, that didn't quite work. If I run this function, longest length, and let's do vec1, vec2. So you see in the function definition a variable L1 and a variable L2, but these variables are not going to exist once this function is over. So even though I just ran this function, there's no such thing as, I guess I declared L1 at some point. I don't remember when it was, but L2 is not a thing. So, you just because there are variables declared in here, they're basically visible to the function only. What ends up with this function, I create a variable L1, L2, and then return the maximum of these two things. So since this is the last call in the function and it's not assigned to anything, like if I did, for example, x, like this, and then I create this function, and then I do longest length, vec1, vec2, it doesn't return anything. But since I don't assign it to anything, it ends up getting returned. Another option would be to do return, like so. And we've also got a bunch of comments in this function. And then I do longest length, and that works the same way. Okay, so that's basically how a function works. You're probably going to find even in this class, you're probably going to write a number of functions. If you walk out of this class and you don't know how to create a function, then I have failed you. So that's how functions work. That's how functions are made. That's kind of the basic idea of a function. If you want, I can make another function right now. So f will be a function. This function has no parameters. All it ever does is return the number 1. So f 1. All right. So some more examples. Here we have our longest length function, and it gives us some output, and so we have a couple options when passing values to a function. We can either pass them positionally, where the element, where whatever we pass in the first position will be the first argument, and whatever we pass to the second element is going to be the second argument. So vec1 corresponds to x, and vec2 corresponds to y in this context. But if we want, we can explicitly say that y will be vector 2 and x will be vector 1. Now, in this case, since we're just taking the maximum of two things, it doesn't seem to really matter the order in which we pass arguments, but in general, it does matter. The order does matter. Okay, so far, all we have really been talking about is R programming basics. The painfully boring topics of subsetting vectors and vector-wise operations and booleans and all that stuff. It's honestly super boring. I'm not going to pretend that this is exciting stuff. It is not. Now we can actually talk about some statistics, which is a little bit more interesting. This is at this point, though, these statistics, you basically just, what is the appropriate function for what you want to do? So talking about actual univariate data analysis, we're going to go through all the stuff that I talked about in chapter 1 of Dr. Fazani's book. No, Dr. DeVore's book. So, for example, creating a stem and leaf plot. The function for creating stem and leaf plots is stem. So here's the rivers dataset. Is a built-in dataset consisting of North American river lengths, and it gives us a nice stem and leaf plot for that dataset. We can also create dot plots using the function strip chart. There's a few parameters for this function, such as the method parameter, PCSH, main, and xlab. So main and xlab give the resulting plot some labels. Method is telling us, well, if we were to look at the documentation for strip chart, we can see how exactly the method argument works. Let's see. Method, it's telling us how we should separate coincident points. We could overplot them, we could jitter them, or we could stack them. I prefer, so jittering is like a little random movement. Overplot means that they get put one on top of the other. And I prefer to stack them. PCSH controls the point character, and this is the resulting strip chart. So this is a dot plot for the river lengths. Okay. Let's see. So histograms. The hist function creates histograms. Here is the resulting hist function. Actually, this is some new behavior with R 4.0. Before, by default, R would create white-filled histograms, and everybody said white in your histograms is actually really ugly, and we don't like it. And R 4.0, now the default fill for histogram bars is gray. So my notes are actually a little inaccurate on this because at some point I say, do we really want white bars in our histogram? Well, that's an R 3.0, R 2.0, R 1.0 thing. Now it doesn't do white bars by default. So I guess if you want to see a demonstration, call equals white. That's what it used to look like. That's what it used to look like in previous versions of R, but that is no longer a thing. Okay. But we've got a few parameters that we could set. Like, for example, we can give... let's actually run this again. So R comes up with a default name for our histogram, which we may not necessarily like. It comes up with a default label for the x-axis, a default label for the y-axis. Also is automatically picking a lot of parameters relevant to creating histograms, but we can control those parameters ourselves. Excuse me. We can control those parameters ourselves by setting the main title of the histogram using the main parameter. We can set the x label parameter like so, frequency, right, breaks, and so on. So let's run this code, and here is a new looking histogram. Oops. I closed my R session. Okay. By the way, let's regarding functions, often functions will come with default values. It's actually not too hard to create a function with a default value. For example, f is a function, x equals 1, and x plus 1. This is now a function with a default value for x, which is 1. So I can do f, and I don't actually have to tell R what x is. It will assume, if I don't assign it to anything, that it's 1, so this works. But I can also say 2, and now, instead of x being 1, it will be 2. Or I could say, for instance, x equals 2. So actually, these functions, like for example, hist, I can look at what the arguments for hist are using args. It has ellipses for what that means is that it's actually probably a method for something else. So it's going to pass a lot of arguments to a different function. Wonder if a strip chart. Let's try strip chart again. Strip chart. Oh, it's not being cooperative. So these are generic functions. So it's actually passing its arguments on to something else. But a lot of these functions, they actually have a number of parameters that you can set, but a lot of them are already set to defaults, so you don't have to set them yourself. So density curves. Here is some code for creating a density curve. You have to call the density function. So density rivers creates a density object that can represent a density curve. And then when you plot that density object, so I could actually assign this to something. If I then plot G, it will plot a density curve. So, here's some fancy code that will create a histogram, and also on top of that histogram, we can also plot a density curve. And that creates a very fancy looking plot for us and allows us to compare a histogram to a density curve. Box plots, we can create box plots using the box plot function. On its own, a box plot is only mildly interesting. What's more interesting are comparative box plots. So here we have the iris data set. This is containing this classic data set containing data for a sample of iris flowers, sepal lengths, sepal widths, petal lengths, and petal widths. So we can see the sepal lengths of the flowers, and we also have 3 different species of iris flowers: Setosa, versicolor, and virginica. So if we wanted to, we could compare the sepal lengths amongst the species in our data set using this called box plot. And it will create a comparative box plot for us. Bar charts. Central Park Cloud is a data set tracking the cloudiness in Central Park in New York. So a Central Park Cloud. Oh, interesting. Is this an R4.0 thing? Is this no longer? So, does this command no longer work? It doesn't work anymore. Where did Central Park Cloud go? Is it in the, well, I don't know where it went. Central.park Cloud. Oh, that's in the using R data set. Okay. All right, I know what happened. I didn't load in using R. All right, so that's something to look for. Make sure that you have the appropriate libraries loaded. So Central Park Cloud is a using R data set, so I need to actually load in that data set before I can use this function. All right, so you have the bar chart. Central Park Cloud itself is a factor variable, and these are the possible factors. It was just tracking over a period of days, whether it was cloudy or clear over Central Park. You can give that factor variable to bar chart, and it creates a very lovely bar chart for you. Numerical summaries. So for starters, for numerical summaries for univariate data sets, one thing you can start out with is the summary function. The summary function, when given a numeric data set, will tell you a number of interesting statistics for that data set. So, for example, if I pass it the rivers data set, it will give me the 5-number summary and also the mean. Now that said, if I were to pass it a factor variable, what it gives me is a table of counts, because that's pretty much the only thing that's of any interest when you're working with categorical data. You just would look at the frequency counts for each of the possible categories. But in addition to summary, there are functions for specific types of statistics. So, for example, we have a mean function. So the exec.pay dataset, I think that's a using R dataset. So I can ask for the mean of executive's pay, and it will give me the mean. If I wanted a trimmed mean, I can pass a parameter to trim. I can also get the median of exec pay using the median function. There's also a function called quantile and 5num. So if you wanted, say, the 5-number summary for a data set, you can use the 5num function. It will give you the 5-number summary, the minimum, the maximum, the first quartile, the third quartile, and the median. There's also the quantile function for general quantiles. So, for example, if I wanted the 99th percentile for executive pay, it would give me, I could pass 0.99 to the second argument, and it would give me the 99th percentile. By default, it's giving you quantiles, or it's basically equivalent to the 5-number summary. And if I wanted deciles, where you increase by, like, you get the first decile, that's like the first 10% of the population. The second decile, the first 20% of the population is at least this number, and so on. Here is, what just happened? Okay. Here is the deciles for the exec pay data set. So we still have the minimum and the maximum, but we also have the 90th percentile, the 80th percentile, 70th, 60th, 50th, and so on. There's a quantity in statistics known as the range. The range of a data set is the maximum of the data set minus the minimum of the data set. The range function in R will give you the maximum and the minimum. So if I want the statistical notion of range, I can use this diff function. So diff 1 to 2 will be 1 because it's 2 minus 1. That's how diff works. It subtracts the first element from the second element. So, for example, diff C 1 and 5 will be 4. So if I do diff range, that actually gives me the mathematical notion of range. It's a little surprising, though, that there is an executive in this data set that's making nothing. Anyway, some other basic statistical quantities. We have the variance. If we wanted to get the standard deviation, we could potentially just take the square root of the variance, or we could use the SD function. And I would recommend in general using the SD function. It's probably better than just taking the square root because it was built to compute the standard deviation. And it probably will be like more numerically accurate. For categorical data, there's really only one way to really summarize categorical data, and that's with a table of counts. So we can use the table function to get such a table. And if we wanted frequencies, like relative frequencies, we could divide by the length of the vector, and that would get us relative frequencies. So these numbers would add up to 1. I can even check that by passing this to sum, and it adds up to 1. Whereas if I were to work with the original data and do sum, it would add up to the length of the vector. All right, this video has gone on long enough. I am so done with this lecture, and so I will see you later.